All right, let's jump right in and tackle a real classic from Irodov's problem collection, number 1.79. Now, I know this one can look a little scary at first because it mixes acceleration, friction, and multiple bodies all into one. But trust me, we're going to break it down step by step, and you'll see it's totally manageable. Let's get into it. So here's the setup. We've got two identical masses. They're connected by a string that goes over a nice, frictionless pulley. One mass is hanging against a vertical wall, the other is sitting on a horizontal surface. And this whole shebang is on a big bar A, that's being accelerated sideways. The question is, what's the minimum acceleration we need to give this bar to keep those two little blocks from sliding around? I know. Your first reaction might be that this looks like a mess. You've got things moving, forces pointing every which way, friction. It's a lot. But here's the secret to pretty much all of these tricky physics problems. It's all about finding the right way to look at it. If you can find the right perspective, the complexity just melts away.
And that brings us to our big strategy for this problem, picking the right frame of reference. This is without a doubt one of the most powerful tricks you have in your mechanics toolkit. Instead of standing on the ground watching this whole chaotic scene whiz by, what if we could just hop on the bar and ride along with it?
This right here shows you why that's such a game changer. If you're on the ground in what we call an inertial frame, you see bar A accelerating, you see bodies 1 and 2 accelerating along with it, it's a dynamics problem. But if we switch our perspective and imagine we're standing on bar A, the non-inertial frame, well, from our point of view, the bar isn't moving. And the problem tells us the two bodies are also stationary. All of a sudden, this messy dynamics problem turns into a simple equilibrium problem, where all the forces just have to balance out to zero. That is so much easier. Now, there is a small price to pay for this amazing simplification. It feels a little like cheating, but it's perfectly valid. To make Newton's laws work correctly in an accelerating frame, we have to invent a new force. We call it a pseudo-force, or an inertial force. Think of it as a correction factor that lets us use our simple equilibrium rules. So, what is this pseudo-force? It's basically a force that everything inside the accelerating frame feels. Its size is easy. It's just the mass of the object, m, times the acceleration of the frame, which we're calling w. But the direction is absolutely key. It always points in the direction opposite to the real acceleration of the frame. So if bar A is accelerating to the left, everything on it is going to feel a pseudo-force pushing it to the right. Okay, strategy's locked in. We're using the accelerating frame. The next step, as with any forces problem, is to draw our free body diagrams. We need to identify every single force acting on our objects. This is like creating the blueprint for our entire solution. Let's zoom in on body 1 first, the one that's pressed up against the vertical face of the bar. Let's isolate it in our minds and figure out everything that's pushing or pulling on it. Okay, let's walk through it. Gravity, mg, is easy. It pulls straight down. Now, because of gravity, this block wants to slide down. So the friction force has to oppose that, which means friction, FFR1, points up. The string is also pulling up, so that's our tension T. Now for the new stuff. To keep the block from sliding down, we need more friction, which means we need a bigger normal force. To get a normal force, we have to squish the block against the wall. We do that by accelerating the whole bar to the left. This creates our pseudo-force, mw, pushing the block to the right. And of course, the wall pushes back. That's the normal force, N1 pointing to the left. Got it? Perfect. Now let's do the exact same thing for body 2, the one sitting on top. For body 2, gravity, mg, pulls it down. The bar's surface pushes up with a normal force, N2. The string is pulling it to the left with tension T. And just like before, because the whole frame is accelerating left, there's a pseudo-force, mw, pushing body 2 to the right. Now think about friction. The tension is trying to drag this block to the left. To stop that from happening, the friction force, FFR2, has to pull in the opposite direction, so it points to the right. So for this block, both friction and the pseudo-force are teaming up to fight against the tension. All right, we've got our force diagrams, the pictures are done. Now it's time to translate these pictures into the language of physics, which, of course, is math. We're going to write down our equilibrium equations for each body. And don't forget why we're allowed to do this. The whole point, the magic of using the accelerating frame, is that in this frame, the blocks are not moving. They're in equilibrium. And that means if you add up all the forces pointing left and right, they have to sum to zero. And if you add up all the forces pointing up and down, they also have to sum to zero. And this table is our masterpiece. It's the entire problem laid out in 4 simple equations. Let's quickly check them. For body 1, horizontally, we have the pseudo-force Mw pointing right, balanced by the normal force N1 pointing left. So Mw minus N1 equals 0. Vertically, we have tension and friction pointing up, balanced by gravity pointing down. So T plus FFR1 minus Mg equals 0. For body 2, horizontally, the pseudo-force and friction both point right, and they balance the tension pointing left. So Mw plus FFR2 minus T equals 0. And vertically, the normal force N2 up balances gravity Mg down. N2 minus Mg equals 0. Perfect. This is our roadmap.
Okay, the physics part is officially done. We've set everything up. The rest is just algebra. So let's put on our algebra hats and solve this system of equations to find what we're looking for, that minimum acceleration W. Now pay close attention to this word from the problem, minimum. This is a huge clue. If we're using the minimum possible acceleration, it means our system is on the absolute brink of slipping. It's holding on by a thread, and that tells us that static friction is working as hard as it possibly can. It's giving us its maximum effort.
And lucky for us, there's a formula for that maximum effort. The maximum force of static friction is simply the coefficient of friction, K sub s, multiplied by the normal force N. This is the key that unlocks the rest of the problem. We can now replace our FFR terms with K sub s times N.
So here's our game plan. Step 1, let's find the normal forces. From our equations, this is super easy. N1 equals Mw, and N2 equals Mg. Step 2, let's find the max friction forces. FR1 is just K times N1, so it's K times Mw, and FR2 is K times N2, so it's K times Mg. Step 3, we plug these expressions for friction back into our 2 main equations. Step 4 is the really clever part. We have 2 equations, and they both have tension T in them. We can rearrange them and add them together in such a way that the T's just cancel each other out. It's a beautiful trick. That leaves us with just 1 equation, and the only thing we don't know is W. So for step 5, we just do a bit of algebraic shuffling to get W all by itself.
And voila, there is our answer. The minimum acceleration, W, is equal to g times the fraction 1 minus k over 1 plus k. Notice anything cool? The mass, m, completely canceled out. It doesn't matter if the blocks are heavy or light, the required acceleration is the same. It only depends on gravity and how sticky the surfaces are. Pretty elegant, right? But hang on, we're not done yet. Getting the formula is great, but really understanding what it's telling us, that's the whole point of doing physics. So let's dig into this answer a little bit and look at some common places people trip up.
So here are the big traps to watch out for on a problem like this. Number 1, by far is just forgetting the pseudo-force. If you use an accelerating frame, you must add that force. Second, getting the direction of friction wrong. Always stop and think, which way does the object want to slide? Friction will always oppose that. Third, not realizing that minimum acceleration means you have to use the maximum static friction formula, FFR equals K times N. And finally, of course, just be careful with your algebra. It's easy to drop a sign here or there. Let's test our formula. Let's ask it a silly question and see if it gives a sensible answer. What happens if K, the coefficient of friction, is equal to 1? Well, if you plug K equals 1 into our formula, the top part, 1 minus K, becomes 0. That means the whole acceleration W is 0. What does that mean physically? It means if the surfaces are really, really sticky. If K is 1, the static friction on body 2 is already strong enough all by itself to hold up body 1. You don't need to accelerate the bar at all. The system is perfectly stable just sitting there. See? The math gives us an answer that makes perfect physical sense.
And I'll leave you with one final thing to think about. What if the problem was slightly different? What if the friction coefficient was K1 for the vertical surface and K2 for the horizontal one? How would our solution change? Well, the amazing thing is the overall approach, the strategy, would be exactly the same. You'd still use the non-inertial frame, you'd still add a pseudo-force, you'd still write your equilibrium equations. The only thing that would change is a little bit of the algebra at the end. Mastering the method is what really matters.